The deep dive. If you're preparing for exams, competitive ones like UPSC, SSC, state PSCs, or maybe your class 9, 10, 11, or 12 boards, you're in the right place. Today, we're tackling three really crucial concepts in physics: work, energy, and power. We're going to break them down, look at the definitions, the formulas, practical uses, basically everything you need to ace those questions.
Absolutely. And it's important to see how they connect: work, energy, power. They build naturally on what you've learned about motion, force, even gravitation. It gives you a much more, holistic view of physics.
Right, so let's start with work. Now, we use this word all the time in daily life. I worked hard today, but in physics, it's very specific, isn't it? Can you clarify that distinction? It seems vital for exams.
Yes, it's a common confusion spot. Everyday work might be studying hard, like Kamali in the example, or pushing a huge rock without it moving, or even just standing still, holding something heavy. You feel tired, you feel like you've worked. But scientifically, often in those cases, zero work is done. Physics has strict conditions.
Okay, so what are those conditions?
Two things. Absolutely essential. First, a force has to act on an object. Makes sense. Second, and this is key, the object must be displaced. It has to move. And crucially, it needs to move because of that force, or at least have a component of motion in the direction of the force.
So if there's no movement, like the rock example, then no work.
Exactly. No displacement, no scientific work done on the rock. Same if Kamali is studying, her mental effort isn't displacing the books by her own force, or holding a heavy bag perfectly still on your head effort, yes. But no displacement of the bag, so no work done on the bag by you against gravity. But if you push a small pebble and it rolls, work is done. A girl pulls a trolley, it moves. Work is done. You lift a book, it moves upwards due to your upward force. That's work. Getting this distinction right is fundamental for problem solving.
Okay, that makes the definition much clearer. So if work is done, how do we actually calculate it? What's the math behind it?
For a constant force, it's quite straightforward. Work, usually written as W, is the product of the force, F, and the displacement, S. So W is FAS. The standard unit, the SI unit, is the joule, symbol J. 1 joule is defined as the work done when a 1 Newton force moves an object 1 meter in the direction of the force. So 1 joule equals 1 Newton meter.
Newton meter, got it.
And remember, work is a scalar. It has magnitude, how much work, but no direction.
Okay, and you mentioned zero work conditions.
Yes, 3 key situations for zero work. 1, no force is applied, S0. 2, no displacement occurs, S0. 3, and this is important too, if the force is acting perpendicular, exactly 90 degrees to the direction of displacement. Think of carrying a suitcase horizontally. Your lifting force is up, but the movement is forward. The lifting force does no work in the horizontal direction.
Right, that perpendicular case is interesting. Now, what about positive and negative work? How does that work?
Good question. Work isn't just about magnitude. Its sign tells us something important. Positive work happens when the force, or a component of it, acts in the same direction as the object's displacement.
Like pushing something forward.
Exactly. Or like the example of a baby pulling a toy car straight ahead. The pulling force and the car's motion are aligned. Positive work means energy is typically being transferred to the object. Negative work, on the other hand, occurs when the force acts opposite to the direction of displacement. The angle is 180 degrees.
Like friction slowing something down.
Precisely. Friction opposes motion, so it does negative work, removing energy from the object's motion. Another common example, lifting an object. The upward force you apply does positive work, but gravity is pulling down while the object moves up. So the work done by gravity in this case is negative.
So the same action can involve both positive and negative work, depending on which force you're looking at.
Exactly. You have to be specific about which force is doing the work. Let's take that porter example. He lifts 15-kilogram luggage 1.5 meters up. We need the work he did.
Okay, so force times displacement.
Right. First, the force. He has to lift against gravity, so the minimum force is the weight of the luggage. Mass is 15 kilograms. Let's say G is 10 meters SOSIT for simplicity here. Force equals 15 kilograms, 10 meters SOSIT, and Leonard for 150 newtons.
Okay, 150 N.
Displacement is 1.5 meters upwards. So work force X, displacement equals 1.5, and it's 1.5 meters with 225 joules. And it's positive because his force is up and the displacement is up.
225 joules.
Yeah.
Makes sense. Okay, from work, let's naturally bridge over to energy. It feels closely related. How do we define energy scientifically?
Yeah.
And where does it come from?
They are incredibly related. Energy is defined fundamentally as the capacity or the capability to do work. If an object possesses energy, it has the potential, you could say, to exert a force over a distance.
So work is energy transfer.
Essentially, yes. When work is done, energy is transferred. The object doing the work loses energy, and the object on which work is done gains it. And because of this direct link, the unit for energy is also the joule, JJ. 1 joule of energy allows for 1 joule of work to be done. And we often use kilojoules, KJ, for larger amounts. 1 kiloj is the 1000J. As for sources, well, the biggest natural source for us here on Earth is undoubtedly the sun. Almost all our energy ultimately traces back to it. But we also harness energy from atomic nuclei, that's nuclear energy, and from the Earth's internal heat, geothermal energy. Tides, too. You see energy manifest when objects gain the ability to do work. Think of a fast cricket ball. It has energy to knock over the wickets. A raised hammer has energy to drive a nail when it falls. Even a wound-up toy car spring stores energy.
Right, energy seems to be everywhere in different forms.
Exactly. Energy isn't just one thing. It comes in various forms. For exams, knowing the main ones is crucial. There's mechanical energy, and that's a big one we'll break down into potential and kinetic energy. And then you have heat energy, chemical energy, like in batteries or food, electrical energy, light energy, many forms. Each represents stored or moving energy capable of doing work.
Okay, let's dive into mechanical energy then. Started with kinetic energy. What's the definition there?
Kinetic energy, often shortened to KE, is simply the energy an object possesses because it's moving. If it has velocity, it has kinetic energy.
So anything moving, a car, a ball, wind.
A falling coconut, a speeding car, a rolling stone, flowing water, blowing wind, a running athlete, yes, all possess kinetic energy. And a key point, kinetic energy depends strongly on speed. It increases with the square of the velocity, double the speed, quadruple the kinetic energy.
The square, okay. And how do we calculate it? Is there a formula?
There is. The kinetic energy of an object is given by Ke equals mv/n, where m is the object's mass and v is its velocity or speed.
Half rum v squared. Where does that come from?
It comes directly from the definition of work. The kinetic energy gained by an object is equal to the work done on it to accelerate it from rest to velocity v. If you use the equations of motion, specifically vu weak equals 2a's and set initial velocity u equals 0, you get v was 2a's, or sx equals v for 2a. Then work equals force x displacement equals b. The a cancels out, leaving w equals half dem vuo. So the work done equals the kinetic energy gained.
That's a neat derivation.
Let's try a quick example. An object, mass 15 kilograms, moving at 4 meters. It's Ke.
Okay, Ke equals half times 15 kilograms times 4 meters squared. So half times 15 times 16, that's 15 times 820 joules.
Perfect, 120 joules. Now, a common exam style problem. A car, 1,500 kilograms, speeds up from 30 kilometers to 60 kilometers. How much work was done?
So we need the change in kinetic energy. First, convert the speeds, kilometers to amps, multiply by 518.
Exactly. 30 kilometers, 30 18 equals 253 meters, and 60 kilometers is double that, 503 meters.
Okay, so calculate initial Ke with 253 meters, final Ke with 503 meters, and then subtract.
Precisely. Initial Ke equals half 1,553 Abenteuron. Final Ke equals half 1,500 after 3 Nadger. The difference, final Ke minus initial Ke, is the work done. It comes out to 156,250 joules. And just a quick note, the unit joule is named after James Prescott Joule, a British physicist who did foundational work on heat, energy, and their connection.
Good to know. Okay, that covers kinetic energy well. What about the other part of mechanical energy, potential energy?
Right, potential energy, or PE. This is energy stored in an object due to its position or its configuration. It's stored energy ready to be converted, usually into kinetic energy.
Configuration, what does that mean?
Think about stretching a rubber band. You do work on it, and that energy is stored in its stretched state, its configuration. Same for compressing a spring or bending a bow before shooting an arrow. That stored energy is elastic potential energy.
I see. Stored due to shape or structure and position. That sounds like gravity might be involved.
Exactly. The most common type we deal with in introductory physics is gravitational potential energy. This is the energy an object has because of its position relative to a gravitational source, usually the Earth.
So lifting something gives it potential energy.
Yes. It's formally defined as the work done in lifting an object from a reference point, like the ground, up to a certain height, h, against the force of gravity.
Now, how do we calculate that?
The minimum force needed to lift an object is equal to its weight, which is mass m times acceleration due to gravity g, so mg. If you lift it a vertical height h, the work done is force x displacement, which gives us the formula for gravitational potential energy. Pe equals meh. Now, a really important point for exams. The value of Pe depends on where you choose your zero level, your reference point. A book on a table has PE relative to the floor, but 0 PE relative to the table itself, if that's your reference.
Okay, so the reference matters.
It does for the absolute value, but the change in potential energy and the work done by gravity only depends on the vertical difference in height. It doesn't matter if you lift an object straight up or slide it up a frictionless ramp to the same final height. The gain in gravitational PE is exactly the same, ME. The path doesn't matter for the potential energy change against gravity.
That's a crucial point. Path independence. Got it. Can we do a quick example?
Sure. Let's find the PE of a 10-kilogram object held 6 meters above the ground. Assume G equals 9.8 meters circs.
Okay, PE equals MEH. So 10 kilograms times 9.8 meters times 6 meters. 10 times 6 is 60. 60 times 9.8, nearly 600.
588.
Exactly right. 588 joules. Now flip it around. An object mass 12 kilograms has 480 J of potential energy. If we use G equals 10 meters circs, how high is it?
Okay, P equals MEH, so SPE mg. That's 480 J divided by 12 kilogram times 10 meters stirs. 480 divided by 120. That's 4 meters.
Perfect. Do you see how these calculations work? They're standard types you'll encounter. Definitely. So we have kinetic energy, motion, and potential energy. Position configuration. They seem to transform into each other. Like when something falls, PE becomes KE. Does the total amount of energy change during these transformations?
That brings us to perhaps the single most important principle regarding energy, the law of conservation of energy.
Sounds fundamental.
It is. It states that energy cannot be created or destroyed, only converted from one form to another. In any closed, isolated system, the total amount of energy remains constant. Always. It just changes its form.
Always constant. So energy is never lost.
Well, in real-world scenarios, energy might seem lost due to things like friction converting mechanical energy into heat, which dissipates. But the total energy, including that heat, is conserved. For simplified physics problems, especially involving gravity, we often ignore air resistance and friction. Consider the classic example, a freely falling object. Let's say you drop a ball from height. At the very top, just before release, velocity is 0, so KE equals 0. All its mechanical energy is potential. PE equals MEH. Total energy equals MEA. As it falls, H decreases, so PE decreases. But its speed V increases, so KE MBA increases.
Right, PE converts to KE.
Exactly. And just before it hits the ground, H0, PE is nearly 0, and velocity is maximum, so KE is maximum. The key insight from the conservation law is that at any point during the fall, the sum of its potential energy and kinetic energy remains constant. PE plus KE equals constant, or MEH plus MVI equals constant. This total mechanical energy is conserved if we ignore air resistance.
That's a powerful idea for solving problems, knowing the total energy stays the same.
Immensely powerful.
Okay, fantastic. We've covered work, kinetic energy, potential energy, and conservation of energy. Let's move to the last piece. Power. We hear about powerful engines, powerful people. How does this relate to work?
Power relates directly to how fast work is done or how quickly energy is transferred. Doing a lot of work slowly might not be very powerful. Doing the same work quickly requires more power.
So it's about the rate.
Precisely. Power P is defined as the rate of doing work or the rate of energy transfer. The formula is simple. Power work time, or P equals W a teat. The SI unit for power is the watt, W, named after James Watt, the steam engine pioneer. 1 watt means work is being done at a rate of 1 joule every second. So 1 W is 1 JS.
Joules per second. Okay.
And you often see kilowatts, kW, for things like engines or heaters. 1 kilowatt is 1,000 watts, meaning 1,000 joules transferred per second. If the power isn't constant, we can talk about average power, which is just the total energy transferred divided by the total time taken.
Right. So power tells us how quickly energy is used or work is done. Let's try some examples to make sure we've got it.
Okay, classic comparison. 2 girls, A and B, both weigh 400 newtons. Both climb a rope 8 meters high. Girl A takes 20 seconds. Girl B takes 50 seconds. Who is more powerful?
Okay, well, they do the same work, right? Lifting their weight 400 N through a height, 8 meters. Work hour X displacement equals 400 N, 8 meters, equals 3,200 joules for both.
Correct. The work done is identical.
Now, power is work time. For girl A, power equals 3,200 J20S equals 160 watts. For girl B, power equals 3,200 J50s. 325, 64 watts.
Exactly. So girl A is significantly more powerful because she did the same work in less time.
That makes the difference clear.
Another one?
Sure. A boy, mass 50 kilograms, runs up 45 steps. Each step is 15 centimeters high. He takes 9 seconds. Find his power. Let's use G. It's a 10 meters on us.
Okay, first find the total height. 45 steps times 15 centimeter step. 15 centimeters is 0.15 meters. So 45, so 0.15 meters.
Okay.
6.75 meters.
Correct. 6.75 meters is the total vertical height.
Next, the work done. He's lifting his own weight up that height. His weight's 50 kilograms, 10 meters times 500 newtons.
Right.
So work A's height, hefty height, based on 500 and times 6.75 meters. 500 times 6 is 3,000. 500 times 0.75 is 375. So 375 joules.
Excellent calculation. 375 joules.
And finally, power work time equals 33375 J9s. Okay, 375 divided by 9, 375 watts.
Spot on. 375 watts. See, by breaking it down, find height, find work, which is PE gain here, then divide by time, you can solve these multi-step power problems. Fantastic. That really ties everything together. So to wrap up this deep dive, we started with work. Nailing down that scientific definition, force and displacement are needed. We looked at positive, negative, and zero work. Then we moved to energy, the capacity to do work. We explored different forms, focusing on kinetic energy due to motion, and potential energy, especially MI, due to position.
And crucially, the law of conservation of energy transforms, but the total amount stays constant in a closed system.
Yes. And finally, power, the rate at which work is done or energy is transferred, measured in watts, LWTS. These are all absolutely fundamental for physics and, of course, for your exam.
They really are. And understanding how they interlink, how work changes energy, how power describes the rate of that change is key. I really encourage you, as you study and even just look around, try to see these principles in action. Visualizing it helps tremendously.
Great advice. Remember, everyone, follow us for more content like this, designed to help you excel. Stay tuned for more exam-ready insights. In this deep dive, we comprehensively covered the following topics: the scientific definition of work, positive, negative, and zero work, the concept of energy and its forms, kinetic energy and its calculation, potential energy and its calculation, the law of conservation of energy, power and its measurement,